Okay. Hi, everyone. It's me again. So we had some technical problems this morning, which means I'll record the lecture again, and they've got about 45 minutes to do it. So it will be a bit tight, which means we only have one chance to get it right. Good. And today is lecture 10, and we'll continue talking about the particle in space. And so far, everything is one dimension. And today we're going to apply the Schrödinger equation to the wave function to see how the wave function evolves. And then we're going to do it more explicitly for the simplest Hamiltonian we can have, which is when this potential is zero. Okay? So we'll see in that case how one of the wave functions evolves in time, and then we'll continue next week with more details. So let me just very good. I've got all the notes of next week's lecture. Yeah. Last week's lecture. All right, so let's start with what we did last time. Okay, so last time we've been looking at Hamiltonians of the form h is the momentum square over 2 times the mass of some particle of our system, plus some potential that depends on the position. And this first term here is the kinetic energy, whereas this term here is the potential energy. And what I mean by V of x is simply that this is going to be a matrix that's diagonal in the position basis. Okay, so by this, I mean that it's something in the x basis, and it will have some value depending on the position. Okay, good. And we saw how the position and the momentum evolve on average. So this was this Herrenfest theorem, which went like this. So the derivative of the position, that was the rate at which the position changes at a given moment in time, depends on the momentum divided by the mass, which is classically, it corresponds to the velocity of the system. And likewise, the derivative of the momentum depends on the force felt by the system, which is kind of the gradient of this potential at a given time. So, and thank you to Mark, who found all the missing minus signs. So to give you an idea of why this is minus, if you think classically, suppose that this is x. So just think of gravitation, the gravitical force on Earth. So if you have a body here, the potential energy is given by m times x being this position times this constant, the gravitational constant. But the force, of course, v of x gets higher the higher the object is, and the force is minus mg, which is a derivative of this potential in order to x with a minus sign, because the force is always pulling against the potential gradient, right? It's what think of it as really the force that the object feels in the classical case. And we saw that in general, if you want to know how the average of some observable changes in time, this was I over h bar HA, and then you can replace these things for this particular potential Hamiltonian. So by the way, this kind of kinetic energy corresponds to indeed massive particles, maybe we'll see later that for a photon, for example, it's a different thing here. You don't have p squared, but only p. Depends on p. Okay. So let's, the last thing we did was Schrödinger's equation, which was, and last thing we'll need now is this. Okay, it tells us the rate of change of the state depends on the Hamiltonian. And what we'll do today is to see, well, I want to know if the state evolved, but instead of looking at the whole vector at once, I just want to know how it changes in a given basis. So I just want to know how the x changes. So I just put here this vector, and if the equation that's white is true, then if I multiply left and right by the same vector, it's still true, right? So if we continue, so this is x. Thank you. Copy. So this is x. And now we write here a Hamiltonian. P squared. Did I have the 2 before? Yes. Plus v of x of t equals, and on the right, I h bar. The thing is that the x, think of it like the ruler that tells me at what position I'm looking at. So this ruler does not depend on time. It's just always there. It's just telling me what position in space I'm looking at. So we can, for the perspective of this derivative, this is just a constant, even though it's a constant vector. So we can bring it to the other side. So we have d dt of x psi of t. Okay, so now we have some terms here to work with. So x, so 1 over 2 mu of x p squared of t plus x v of x psi of t equals I h bar d dt. But this thing here is just a wave function. So this here is just by definition the wave function. And because it depends on time now, we put it explicitly here, right? So it's something that depends on the position and on time. And remember, this is just a complex number. Okay, so we have 2 things to take care of now. So we need to compute this. It's going to be number 1. And this is going to be number 2. I think I gave him different names in the lecture notes, but I'm sure you can follow along. I think it was 2 and 3 respectively. Okay, so we start with number 1. So we want to know x p squared psi. I omit the t dependence for now because it's easier to write. And what do we know? Well, we know from before, from previous classes, this one with only 1p. And this was, I want to say minus I h bar d dx of the wave function, right? Remember when we saw last week how the momentum operator acts on the wave function? We computed exactly this quantity here. So we know that, but we want to compute it with p squared. So what we do is we just separate the two p operators. So I'll write it here for you. So we say this is x, 1 p operator, another p operator, psi, and this is a general trick we'll use a few times. We put an identity here, right? The identity is not doing anything. Here on the right are all the tricks we use. Now, the identity can be written in any basis, like so. Sorry, I want x here. Dx, x. Okay, it can also be written as dp EV, and in any basis it can do this. And because one of the students did not believe me in the class, so it will be an exercise next week to prove this. Okay, so you look at tutorial 6 to see the proof of this. Good. Okay, so we insert this here on the left. So we have x and p. We leave it alone for now, and now we put here this thing. I'll make it in green. Dx, and I'll just put x prime so that we don't confuse it with the other x. And now we have here x prime, and then what we had there before, p, check. And the nice thing is that this thing here, we know because we just told it before, right? So by putting this identity here, you split this thing that you didn't know into two pieces that you know. The next one, we'll see that it will be easy to take care of. Okay. So this is minus I h bar ddx of the wave function of my state at time at position x prime. Good. So let's write it down here. So we have x p. Now this integral dx prime x prime, and now this thing here. Okay. Now, if you look at it, so this is the integral over a basis of the basis vectors times the coefficient. This coefficient is like a wave function. It might not be normalized, so it's not a physical state, but it's still expanding a vector in this basis, which means that we take here, we're just going to call it the new wave function at some point psi prime, and it's the wave function x prime. So this means that we can define a new state, check psi prime, which is just okay, it's just this thing. I changed the name of the integration variable, doesn't change anything, which means, so that covered this whole thing here on the right is just psi prime. It's just on your state. So we have what x p psi prime Okay, I think we're live again. All right. Okay, so let's try to do this again. So what was I saying? I said we're back here, so we can replace this in a product with this formula that we learned before, where now the wave function here is this new wave function that we computed just before, this green thing there. So now we can just replace it here. So let's do that. So that's minus I h bar d dx of minus I h bar d dx of their original wave function. So that's minus h bar square d dx second derivative of the original wave function. Yeah. We will come back to it later. I know it's a bit ugly there in the corner, but we'll come back to it. Okay, let's do the second part. So this was part 1. And now we need to deal with this element here. And then we'll come back here. And this one is very simple because we just have x, v of x, psi. And remember that I told you that v of x is just, it's diagonal in the position basis. Okay, so v is some real number at position x prime. Okay, so we just replace it here. Let me just get it a different color. Got it. Okay. So we have x, this integral dx prime. I'm just using a different name for the variable. This v of x is just a number, a real number at that, and the state again. And the integrals always go from minus infinity to plus infinity. If for some reason it doesn't, I'll tell you. Otherwise, if you don't see the limits, assume that it's a typo. Okay, so now we have two things here. One is we have x prime. Then we have x prime and psi, and then we have this number here still lying around. Okay. So this we know is the Dirac delta, and this we know it's the wave function. Right. Position x prime, which means the way the Dirac delta works, if you remember, is that this whole integral evaluates to just the value of what's inside, which is this and this at point x, right, at this point. So with all this, we get, we get rid of the integral. V of x is a number, and then we have also the x prime is a number, x prime there, psi of x. Okay, let's bring it together. I'll copy this equation here to the next page. Okay, so now we have this, right? So with the things we already computed, what we get is 1/2 mu, and what we got here was minus h bar square d square of psi of x plus v of x psi of x. And now maybe it's better to make the time dependence explicit. X and t equals I h bar d dt psi of x and t. Yeah. So let's just simplify here on the left. Let me just put this here. Okay. Now this is the Schrödinger equation for the wave function in general. And now we're going to just quickly look at the case at what happens when v of x is 0. So let me just Maybe I'll copy it. And it will make sense in a moment. We'll call it the wave function. So the simplest case now is the free particle. Which means this potential is 0. It only has kinetic energy. Think of it like you throw a ball and the ball is just moving in space, in outer space, no force is acting on it, or an electron, you shoot it, and it only has like the inertia of its own mass, and that's it. Okay? No gravity, no nothing. Okay, so in this case, first, what happens to the wave function, to the position wave function? Well, we just lose this middle term here because v of x is 0. So we get this. And now if we just simplify it by just I put only the time derivative on one side. Whoop. So we get dt of this function that depends on the position and time is, let's see if I get this right. H of r over 2. Like that. X and t. Okay. Let me see if I got. Might be a minus sign, but we'll. So this might be plus or minus. I don't know. So work it out for ourselves. It's a good exercise. Okay, so what we learned from here, well, on the left we have the time derivative of function, and on the right we have the second derivative, but not in order in time, in order of position. Okay, and some complex factor behind. And what is special about this equation is that it's exactly the same differential equation that governs the behavior of waves. So if you think of sound waves or waves in a pool, water waves, then they are their physics and their classical object, but their physics is governed by an equation that's exactly like this, with the time derivative on one side and a double position derivative on the other side. Which is why we call these coefficients the wave function. It all comes from this example. And that's why we've been all along calling it the wave function. So I'm happy to clarify this. Now, there's much more that we can say about this case of the Hamiltonian of the free particle. I mean, we could solve this differential equation directly, but it's a bit complicated, right? You have to do this double derivative. And if you don't know it, it's hard to guess what it would be. So we're going to do something much easier, which is we're going to look at the momentum basis. And why does that make sense? Well, it makes sense because the Hamiltonian is just p squared over 2m, 2 times the mass. And if you want to make this explicit, well, let's make it explicit. So it's 2. And now we have 2 momentum operators, so let's write them down. The momentum operator is this. And now another copy, and I'll just give a different name to the integration variable. Okay, so this is just a definition of the okay. So this is P, and this one is P2. It's just a definition of this operator. So what happens now? When we multiply them, we get 1 over 2 mu. And then we get these integrals, one integral in dp, one integral dp prime, p prime, these are just real numbers. And then we have p prime, P prime. But this we know that this is the Dirac delta again. So we get rid of one of the integrals for free. So we end up with 1/2 mu integral of dp p squared. So this all to tell you what you could maybe intuit by looking just this, which is that this Hamiltonian is diagonal in the momentum basis, right? So this is the momentum basis, and you can write it in this form. So these are the eigenstates, the energy eigenstates of my Hamiltonian, and these are the eigenvalues. Which means it's going to be much easier to compute the evolution of the wave function in this basis than in the position basis. In the position basis, we'd have to solve this differential equation. Let's see what the differential equation is for the momentum basis. Okay, so evolution of momentum wave function. And here we do again the same trick. So we have the Schrödinger equation equals okay. And now we just plug in here. It's still true if you multiply everything by a vector, and it's going to be the vector corresponding to the position, to the momentum p. So then what we get, so if you replace the Hamiltonian, we get here 1/2 mu p squared psi of t equals, and on the right again the momentum does not depend on time, so the momentum basis does not depend on time, so we can move it to the right, p psi of t, right? So this is just the momentum wave function. Yep. If you don't remember what it is, go see 2 lectures before when we defined it. And now we need to deal with this one here. And we're going to use exactly the same trick as before. So okay. So this was number 1. We need to solve this. P squared psi. I'll omit the dependence in time for now, for simplicity. And what we know is this one, when we have only one p operator. And it was just p and the wave function, the momentum wave function, right? Okay, so we're going to do exactly the same. We're going to say, well, this is the same as p, one of the p operators, and now we plug in here an identity, and we put the other one. And we expand the identity in the basis that is convenient for us, and in this case, it's going to be the momentum basis. Okay, so we'll leave this one alone. dp prime, and just change the name here. And this one is just p times the momentum wave function, right? We just apply this thing here directly. Okay. So then what we do is to define a new state. So we call this one oh, I missed some dashes. Dash. Good. We call this a new wave function because it's just a number that is multiplying this vector, and then this is just a number. So we give it this name, which allows us to define this new vector here, which is just integral dp p, and now this number, right? It's just exactly the same number. I just had to give it here a different name, this p dash, so it's not confused with that. But this is, I just replaced this whole thing with that. Good, so let's do it. So then we have p operator in our new state. And again, we apply this thing here. So this is p times my new wave function, and now I replace with this. So we get p squared times the original momentum wave function. Good, so now we can replace it in our equation, in our Schrödinger equation. So let's see. Okay. So on the right, we had, like I wrote there, just this position. And on the left, we replace with what we just found, which is p squared and the wave function position p, and now I make the time explicit again. Okay. Good, let's tidy things up. So let's put only the time derivative on the left-hand side, and let's see what we get on the right. So we get p squared 2 mu, and here h bar, and goes to the other side, so it becomes minus pi. Okay, and this is again a differential equation. It is again the Schrödinger equation for this case. Okay, but if you compare it to the one for position, let's go back and look at the one for position. It was this here. Oh, here in here in orange. This one is a little bit more complicated because it has this double derivative here. Whereas R1 in the, if you look in the momentum basis, it doesn't, right? It just does the original function. It is much easier to solve. So again, what is the function? Hi, I'm back. I think we had some Wi-Fi problems. Let's see. Okay. So, as we were, what is the function that when we take the time derivative, you get the same function times a constant? It's an exponential. So, which means that I can write the explicit way for the momentum wave function as minus I square h bar over 2 mu. And now comes the variable that I'm deriving in origins of time times some constant. And this constant, you know, if I replace here at p and time equals 0, I get just that constant. So I can just replace here the constant with the wave function at time equals 0. Yeah. So I call it psi 0 of p. So it's a constant in relation to time, right? So this is psi of p and time equals 0. Okay? Which means if I know my initial wave function, that in momentum basis, then I know how to evolve it. Right? Then I know how to evolve it according to this. Very good. Okay, and you can check by just taking the explicit derivative and seeing that it checks out. Good. So now how does the state evolve? We wanted to know how the quantum state evolves, not just this, but you know, you just do it explicitly. T is this unitary that depends on T, psi 0. And now how do we relate it to these things that we just computed? Well, this state psi of 0 of time equals 0 is the integral in p. And now this wave function and now here on the left, the evolved state is same thing. Of P and now E, sorry, of P and T. And now we can replace the P and T there. P and now E, 2 minus, what was it? I h bar P squared over 2. Sorry, the h bar should be on the denominator. Sorry about that. And here again. So I hope you caught that. We were screaming at the screen for the last few minutes. Oh, okay. H bar times. Here's my initial wave function for momentum. Tac. So what's left to do is this U. But we can do directly, and then you can see that it works at home. So in general, we can write it as minus I, the Hamiltonian, time divided by h bar, which in this case is what? Is E 2 minus I p square time 2 root h square, which is exactly, if we expand it in the momentum basis, is going to be pp, and what's in the middle is this coefficient is E little p square t over 2 root h bar. And you can see that if you multiply this matrix times this vector, you get this vector. Okay, so there is something for you to check, like to do this thing explicitly and see that you get this. Good. Okay, so this tells us how the state evolves. And you know, the easiest way to do it was to compute it in the in the diagonal basis of the Hamiltonian. And now, if we want to then express this in any basis, you can by just applying, for example, the Fourier transform or the inverse Fourier transform to this thing here. Then you get the position wave function. So what we will look at next time, let me just see, I didn't forget anything. No. Yeah. So what we'll look at next time is how some physical properties evolve. So something that we can measure, like the average position, the average momentum, and like also the spread in this. And not to give you any spoiler, I mean, yes, to give you spoilers, I'll write here next time. We're going to see how this all works out. And we'll see that what happens to the wave function. So this is x, and here we put the absolute value of the wave function, right? Will tell us the probability of measuring it at a given position. And suppose that at time t equals 0, it is like this. So it's centered around some position. Let's write it, average position at time 0, and it has here some spread, and let's say it's nicely Gaussian, like you did in the tutorial, so this would be delta x. No. Then if it's moving with momentum to the right, what will happen is that, well, the average is going to move linearly. So at some time t prime is going to be there. At time 2 t prime is going to be double the distance, so it's going to be here. However, what the wave function looks like is that it's going to get more spread out. So this was at time 0, and this is going to be t prime. And at some later time, it's going to be even wider. So we're going to compute these things in the next lecture and tutorial. And the kind of the takeaway message is going to be that, well, in some ways, this behaves like a classical particle. You know, if it's moving with some speed, then the position evolves linearly in time. On average, what is different is that it gets more and more spread out. So it's going to be harder and harder to predict where you're going to find the particle if you measure it at some point. Okay, so it's going to get more and more spread out in the position basis. In momentum basis, it's going to stay very neat, very neatly localized. Good. So which means that for this Hamiltonian, the system is not so different from a classical system. And the real differences will be when we start imposing potentials that are non-trivial and drastic. And then we start seeing like what is called quantization. But this is all for next time. And we'll also look at what happens in 3 dimensions and how we can model this. Good. So that's all. Thank you. I hope this worked. I'll have a quick look to see if the recording worked. And if it didn't, then I'll record again tomorrow. Okay. All right.